Welcome! In this session, we will be exploring the problem titled Queries on a Permutation with Key. We'll break down the problem, understand its requirements, and discuss potential approaches to solve it. Let's dive in. In this problem, you are given an array called queries that consists of positive integers, along with another integer n. Using n, we construct a permutation p of the first n positive integers, which starts off as 1, 2, 3, n. The task involves processing each query in the queries array. For each query, you need to find the one-based index of the query value in the current permutation p. Once the index is found, the query value is moved to the front of the permutation, and all other elements are shifted to the right to maintain the order. What you need to return is an array called result, where each element corresponds to the one-based index of the query value in p before it was moved to the front. Let's look at an example to better understand the process. Suppose queries is 3, 1, 2, 1, and n is 5. The initial permutation, p, is 1, 2, 3, 4, 5. For the first query, the value is 3. We locate 3 in the permutation, finding it at index 3. Then, we move 3 to the front of p, which now becomes 3, 1, 2, 4, 5. For the second query, the value is 1. In the updated permutation, 1 is at index 2, so it is moved to the front, resulting in p equals 1, 3, 2, 4, 5. For the third query, the value is 2. We find 2 at index 3 and move it to the front, updating p to 2, 1, 3, 4, 5. Finally, for the fourth query, the value is 1. In the updated permutation, 1 is located at index 2. After moving 1 to the front, the permutation reverts back to 1, 2, 3, 4, 5. The result for this example is 3, 1, 2, 1, as these are the indices where each query value was found before being moved to the front. Now, consider another example. Here, queries is 4, 1, 2, 2, and n is 4. The initial permutation is 1, 2, 3, 4. For the first query, the value is 4, which is located at index 4. Moving 4 to the front updates p to 4, 1, 2, 3. For the second query, the value is 1, which is at index 2. Moving 1 to the front updates p to 1, 4, 2, 3. Next, for the third query, the value is 2. In the updated permutation, 2 is at index 3. Moving 2 to the front changes p to 2, 1, 4, 3. For the fourth query, the value is again 2. Now, 2 is already at the front, at index 1, so the permutation remains 2, 1, 4, 3. The result for this example is 4, 1, 2, 1. Lastly, consider a simpler example where queries is 1 and n is 1. The initial permutation is 1, and for the only query, the value is 1, which is found at index 1. Since 1 is already at the front, the permutation remains unchanged, resulting in 1. The constraints for this problem are as follows. The size of the queries array, m, can be as large as 10,000, and the size of the permutation, 10, can also go up to 10,000. Each query value is guaranteed to be between 1 and n. Let's also consider some edge cases. If there's only one query and one element in the permutation, such as queries equals 1 and n equals 1, the output is simply 1. Another edge case is when all queries are the same, for example, queries equals 2, 2, 2, and n equals 5. Here, after the first query, 2 moves to the front, so the subsequent queries always find it at index 1, resulting in 2, 1, 1. For maximum-sized inputs, the solution must be efficient enough to handle these constraints within a reasonable time. To start, let's examine the brute force approach. The idea here is to simulate the process directly for each query. Initially, we have a permutation p containing numbers from 1 to n in order. For each query, we find the position of the queried number in p, record its index in the result, and then move that number to the front of p by removing it from its current position and inserting it at the beginning. While this approach is straightforward and easy to implement, it has significant inefficiencies. Specifically, finding the index of the queried number takes O, n, in the worst case, and moving the number to the front also requires O, n, operations. With m queries, this results in an overall time complexity of O, m*n, which becomes impractical for large values of n in m. The simplicity of this method comes at the cost of performance, making it unsuitable for scenarios with large input sizes. Now, to optimize the solution, we turn to a more advanced data structure, the Fenwick tree, also known as the binary index tree. The key insight here is that instead of maintaining the permutation array P directly, we can manage the positions of the elements dynamically. A Fenwick tree is particularly well suited for this task because it allows us to perform range queries and point updates efficiently. The process begins by mapping each number, from 1 to n, to its initial position in the permutation. We then use the Fenwick tree to track these positions. For each query, we determine the current index of the queried number using the Fenwick tree, which takes O log n. After recording the result, we update the tree to reflect the process of moving the number to the front. This optimization reduces the time complexity per query to O log n, resulting in a total complexity of O m** log n for m queries. By leveraging the Fenwick tree, we achieve a dramatic improvement in efficiency compared to the brute force method. While the Fenwick tree approach is highly efficient, it does come with added implementation complexity compared to the brute force method. However, the trade-off is well worth it for large inputs. An alternative to the Fenwick tree is the segment tree, which could also handle dynamic position updates and range queries. However, segment trees typically have higher constant factors for their operations, making them less efficient in practice for this problem. Ultimately, the Fenwick tree approach stands out as the most efficient and scalable solution. Unlike the brute force method, which is infeasible for large input sizes, and the segment tree, which has higher overhead, the Fenwick tree strikes the ideal balance between speed and complexity. By using this strategy, we can efficiently handle the dynamic updates required by the problem while staying well within the constraints, making it the optimal choice for solving queries on a permutation with key. In this problem, we are tasked with simulating a process involving a permutation of integers. The initial permutation, denoted as P, consists of integers from 1 to n in ascending order. Alongside this permutation, we are given a list of queries, where each query specifies a number. For every query, the goal is to locate the queried number in the permutation, record its current index in a zero-based format, and then move that number to the front of the permutation. Ultimately, we need to compile and return a list of these recorded indices in the order the queries are processed. To begin with, we initialize the permutation P as a list of integers from 1 to n. Additionally, we create an empty list called result to store the indices as we process each query. Now, as we process the queries, the algorithm follows a structured approach. For each query, the first step is to locate the queried number in the permutation P. This can be achieved using a linear search, where we scan through the permutation to find the index of the target number. Once the index is identified, we append it to the result list. After recording the index, we move the queried number to the front of the permutation. This involves two operations: removing the number from its current position using the pop method and then inserting it at the beginning of the list using the insert method. Finally, after processing all the queries, we return the result list, which contains the indices corresponding to each query in the given order. To better understand the problem, let us delve into some key insights. A straightforward implementation of the algorithm, referred to as the naive approach, directly simulates the process described. However, this method can be computationally expensive due to its reliance on linear search for locating elements, especially as the size of the permutation and the number of queries increase. This naive approach has a time complexity of O, q*n, where q is the number of queries and n is the size of the permutation. To address this inefficiency, optimized solutions can leverage advanced data structures like doubly linked lists or Fenwick trees to improve the performance of element lookup and rearrangement. It's also important to consider edge cases, such as a single query with a permutation of size 1, or scenarios where the queries contain repeated numbers. For larger inputs, we must carefully evaluate how the time complexity impacts the overall performance. The choice of data structures plays a significant role in implementing this algorithm. The permutation P is typically represented as a list or array, which allows for dynamic operations like insertion and deletion. The result list serves as the output container for storing the indices of queried numbers. To illustrate the algorithm, let's consider an example where n equals 5, and the query list is 3, 1, 2, 1. During initialization, the permutation P starts as 1, 2, 3, 4, 5, and the result list is empty. From here, we process each query to determine the output. For the first query, the number 3 is located at index 2 in the permutation P. We append this index to the result list, making it 2. The number 3 is then moved to the front of the permutation, updating P to 3, 1, 2, 4, 5. Next, for the query number 1, its index in the updated P is 1. This index is added to the result, resulting in 2, 1. The number 1 is moved to the front, and P becomes 1, 3, 2, 4, 5. The third query, number 2, is located at index 2 in the new permutation. Adding this index to the result gives 2, 1, 2. Moving 2 to the front updates P to 2, 1, 3, 4, 5. Finally, for the query number 1, its index in P is 1. Appending this index results in 2, 1, 2, 1, and moving 1 to the front restores P to its initial state of 1, 2, 3, 4, 5. After processing all the queries, the final result list is 2, 1, 2, 1, which contains the indices of the queried numbers in the order they were processed. It's worth noting that the two key operations in this algorithm are index lookup and list modification. The process of finding the index of a number in the permutation is the most time-consuming step in the naive approach, as it involves a linear search. Meanwhile, modifying the list by removing and inserting elements can also become costly for larger permutations due to the need to shift elements. These operations together contribute to the overall time complexity of the naive solution. To enhance the efficiency of the algorithm, we can explore several optimization strategies. One approach is to use a doubly linked list, which allows for faster rearrangement of elements compared to a standard array. Alternatively, Fenwick trees or segment trees can be used to enable efficient range queries and updates, significantly improving the time complexity of index lookup operations. Another optimization involves caching. If the queries contain repeated numbers, caching their indices can help avoid redundant computations, speeding up the process. A hybrid approach, which combines efficient data structures with caching, can strike a balance between time and space complexities, making the algorithm more suitable for handling larger input sizes. This solution addresses LeetCode problem number 1409, queries on a permutation with key, by simulating the operations on a permutation list. The permutation, initially set to 1, 2, m, is modified for each query. The queried number is located in the permutation, its index is recorded, and the number is moved to the front of the list. The algorithm begins by initializing the permutation array P as a list of integers from 1 to m. It also creates an empty list result to store the indices. For each query, the code uses the index method of the list to find the position of the queried number in P. This operation is O(m) in the worst case since it involves scanning the list. The index is appended to the result list. Next, the queried number is moved to the front of the permutation list. This is achieved by removing the element at the found index using pop and then inserting it at the beginning using insert. Both operations are efficient given the constraints. The process is repeated for all queries in the input list. Finally, the result list, which contains the indices for all queries, is returned. This solution is efficient for the given problem constraints, balancing simplicity and performance by leveraging Python's built-in list operations. Here, we start by importing the necessary packages and defining the solution class. Within the processQueries method, we initialize a permutation list, which will hold the integers from 1 through m, representing the starting state of the permutation. This is achieved by looping from 1 to m and adding each number to the list. We also create an array called result to store the output for each query. Now, we iterate through each element in the query's array. For each query, we find the index of the queried element in the permutation list using the indexOf method. This index tells us where the queried number currently resides in the permutation. Once we have the index, we store it in the result array at the position corresponding to the current query. After recording the index, we remove the queried element from its current position in the permutation list and add it to the front, ensuring that it moves to the start of the list as required by the problem's constraints. Finally, after processing all the queries, we return the result array. This array contains the indices of the queried elements as they were found in the permutation list before being moved to the front. This completes the implementation, efficiently handling the problem's requirements by dynamically adjusting the permutation list for each query. To begin, we are working with the first example where the queries are 3, 1, 2, 1, and the value of m is 5. Initially, our permutation P is 1, 2, 3, 4, 5, and the result list is empty. For the first query, which is 3, we locate the index of 3 in P, which is 2. We append this index, 2, to the result list, making the result 2. Then, we move the value 3 to the front of the permutation, updating P to 3, 1, 2, 4, 5. Next, for the second query, 1, we find its index in P, which is 1. This value is added to the result, resulting in 2, 1. We then move 1 to the front, updating P to 1, 3, 2, 4, 5. For the third query, 2, the index of 2 in P is 2. We append this value to the result, resulting in 2, 1, 2. Finally, we move 2 to the front, updating P to 2, 1, 3, 4, 5. For the fourth query, which is 1, we find its index in P, which is 1. We append this index to the result list, making it 2, 1, 2, 1. Then, we move the value 1 to the front of the permutation, restoring P to its original state of 1, 2, 3, 4, 5. At this point, we've completed processing all queries, and the final output for this example is 2, 1, 2, 1. Moving to the second example, the queries are 4, 4, 4, and m is now 6. The initial permutation P is 1, 2, 3, 4, 5, 6, and the result list is empty. For the first query, 4, we find its index in P, which is 3. We append this index to the result, making it 3. Then, we move 4 to the front of the permutation, updating P to 4, 1, 2, 3, 5, 6. Now, for the second query, which is again 4, its index in P is now 0 since it is already at the front. We append 0 to the result, updating it to 3, 0. Since 4 is already at the front, the permutation remains unchanged as 4, 1, 2, 3, 5, 6. For the third query, which is still 4, the index remains 0. We append this to the result, making it 3, 0, 0. Again, since 4 is already at the front, the permutation does not change. After processing all queries, the final output for this example is 3, 0, 0. In the third example, the queries are 6, 5, 6, with m equal to 6. The initial permutation P is 1, 2, 3, 4, 5, 6, and the result list starts empty. For the first query, 6, we find its index in P, which is 5. We append this index to the result, making it 5. Then, we move 6 to the front of the permutation, updating P to 6, 1, 2, 3, 4, 5. For the second query, 5, its index in P is 5. We append this index to the result, making it 5, 5. Next, we move 5 to the front, updating P to 5, 6, 1, 2, 3, 4. For the final query, which is 6, the index of 6 in P is now 1. We append this value to the result, making it 5, 5, 1. Then, we move 6 to the front, updating P to 6, 5, 1, 2, 3, 4. At this point, we have processed all the queries for this example, and the final output is 5, 5, 1. To analyze the time complexity of the solution, let's break it down into its components. First, the permutation array P is initialized using list, range, 1 in m plus 1, which takes m time because it generates a list of size m with sequential integers. Next, for each query in the queries list, which has a size of n, we perform several operations. Finding the index of the queried value in P using p.index query requires scanning the list in the worst case, which takes m time. Then, the p.pop index operation removes the element at the specified position, which is optimized to run in 1. Finally, the p.insert 0 operation moves the element to the front of the list. This insertion requires shifting all elements to the right, which takes O(m) in the worst case. Adding these together, processing a single query involves O(m) for the search, O(1) for the removal, and O(m) for the insertion, resulting in a total of O(m) for one query in the worst case. Now, if we consider processing all n queries, each taking O(m) time, the overall time complexity becomes O(n*(m). Shifting our focus to space complexity, the primary space usage comes from the permutation array P, which has a size of m, requiring O(m) space. Additionally, we maintain a result list to store indices for the n queries, which takes O(n) space. Since no other significant data structures are used and the auxiliary space is constant at O(1), the total space complexity is the sum of the space for P and result, which is O(m) plus O(n). This simplifies to O max m n, as the dominant term depends on the larger of the two values. Let's examine the best, average, and worst cases for the solution. Even under the best circumstances, such as when the queried element is already at the front of P, the operation p.insert 0 still involves shifting elements, resulting in a worst-case time complexity of O(m) for a single query. For the average case, queries typically require scanning half of P to find the index. However, the insertion and shifting still dominate, keeping the average case time complexity at O(n*(m). In the worst case, the queried element is always at the end of P, and scanning, removal, and insertion all reach their maximum costs, leading to the same overall time complexity of O(n*(m). Compared to a brute force approach that might rebuild the permutation array from scratch after each query, which could result in O(n*(m squared, this implementation is more efficient. However, advanced data structures like Fenwick trees or segment trees can further optimize the process, reducing the time complexity to O(n*(log)m through efficient query and update operations, albeit at the cost of additional space. In conclusion, the current solution achieves a time complexity of O(n*(m) and a space complexity of O max m n. While straightforward to implement, the solution becomes inefficient for large values of n and m, where the cost of operations on the permutation array grows significantly. To handle larger inputs more effectively, optimized approaches using data structures like Fenwick trees or segment trees can reduce the time complexity, though they come with increased implementation complexity. This trade-off between simplicity and performance highlights the importance of considering problem constraints and requirements when choosing an approach. When working on this problem, there are several common mistakes to watch out for. One frequent issue arises from using inefficient search methods within the permutation, such as repeatedly calling index to find the position of an element. This approach results in an O(n) time complexity for each query, which can balloon to O(n squared) for multiple queries. Instead, consider dynamically tracking positions with a more efficient data structure like a dictionary. Another common oversight is failing to update the permutation correctly after processing a query. For instance, if you forget to move the queried element to the front or its designated position, the results will not reflect the intended state. Additionally, edge cases like duplicate queries or a permutation size of 1 are often ignored during testing, which can lead to unexpected errors. Be sure to handle these scenarios carefully. Memory usage is another area to be mindful of. Unnecessary copying of arrays or creating new ones repeatedly can slow down your program. Opt for in-place modifications to save on both time and space. Finally, overcomplicating the logic with extra loops or unnecessary conditions can make your code harder to understand and debug. Strive for a clean, concise solution that adheres to the problem's requirements. Now, let's focus on some insights that are particularly relevant in an interview context. One key observation is the importance of using efficient data structures, such as a dictionary or a Fenwick tree, to dynamically track positions. These structures allow for faster updates and lookups, which are crucial for optimizing your solution. Problems like this often follow a familiar pattern: manipulating and querying data structures efficiently. Take time to practice operations like searching, updating, and reordering elements in arrays or linked lists, as these skills are often transferable to similar problems. It's also important to consider the trade-offs between time and space complexity. While a brute force approach might be easier to implement initially, it's rarely scalable for larger inputs. Efficient solutions typically require additional space for specialized data structures, but the gains in performance are often worth it. During an interview, clear communication is essential. Walk your interviewer through your thought process, explaining how you would optimize from a brute force approach to something more efficient. Be sure to articulate why the optimization is necessary and how it improves the solution's runtime or scalability. This problem also shares similarities with other well-known LeetCode challenges, which can help you draw connections and deepen your understanding. For instance, LeetCode 146, the LRU cache problem, involves reordering elements based on recent usage, a concept closely related to this one. LeetCode 1206, design skip list, focuses on efficient searching and updating within a dynamic structure, offering another useful comparison. Similarly, LeetCode 1670, design front middle back queue, and LeetCode 1244, design a leaderboard, both deal with efficiently managing dynamic sequences of elements. Exploring these problems can help you identify common patterns and techniques. As for alternative approaches, you might consider using a Fenwick tree or segment tree to dynamically track and update positions. These structures can significantly reduce time complexity for certain operations but do require more setup and can be challenging to implement. Another option is a linked list simulation. By leveraging a doubly linked list, you can reorder elements efficiently, though this may use more memory than an array-based solution. Finally, a dictionary-based approach for position tracking is simple yet effective. Mapping each element to its current position allows for O1 lookups and updates, though it does require additional space. Each of these methods has its own strengths and trade-offs, so choose the one that best fits the constraints and requirements of the problem. Great job! To wrap up, we reviewed the problem, discussed the solution, and extracted key learnings. Keep practicing and exploring new challenges. Thank you for joining, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!